Welcome to the online training, Introduction to Hyper-Pipelining. My name is Marlon Price and I will be the presenter for this training. By the end of this course, you will be able to use hyper-pipelining, the second stage of Hyperflex optimization, to boost your Stratix 10 design performance. First, we will define exactly what hyper-pipelining is and how it compares to conventional pipelining. Next, we will demonstrate how to use the reports from the fast-forward compile tool to help you implement hyper-pipelining. Finally, we will go over some things to think about when you begin implementing hyper-pipelining in your own designs. Let's start with hyper-pipelining and how it differs from traditional pipelining. In order to understand hyper-pipelining, let's review how conventional pipelining works. In this example, we have a long delay between two registers. By inserting an extra ALM register stage, we can cut that long combinational path so that the clock can be run at a higher rate. So with the original circuit, we had a long delay of 3.5 nanoseconds for a clock speed of 286 megahertz. By adding the extra register, the 3.5 nanosecond delay has been split into 1.5 and 2.5 nanoseconds. So with the longest register-to-register delay being 2.5 nanoseconds, we can now run the clock at 400 megahertz for a significant 40% gain. But why only 400 megahertz? Why is the longest delay 2.5 nanoseconds when obviously the best performance would be the split, the 3.5 nanoseconds exactly in half? Well, this is where the ALM register's coarse granularity comes in. Because of the delays getting into and out of the ALM register, the compiler cannot place the new ALM register in the exact location it should be for maximum performance gain. A major challenge with conventional pipelining is that traditionally it is done manually. This requires a designer figuring out how many registers need to be added and where in the logic the registers need to be inserted to gain the full benefits of pipelining. So invariably, many design iterations and compilations are required for success. Some designers write their code where they regularly code in multiple register stages throughout the logic. This style works very well in the FPGA, particularly with retiming. But invariably this may be hard to enforce in every logic module, as not all code is written by a single designer or team, and code that is reused from another project may not necessarily follow this rule. The answer to these challenges? Hyper-pipelining. Hyper-pipelining is the process of inserting additional pipeline stages in your design and allowing the hyper-retimer to move them into hyper-register locations for optimal performance gain. How many registers do you add? However many necessary to achieve your target clock rate. Let's return to the 286 MHz design to implement hyper-pipelining. This time, we will add an additional pipeline register to the path. Where we place the new register in the RTL is not as important. This is because we're going to use hyper-retiming to move the register to its optimal location in the path. Since there are hyperregisters all along the path between the two registers, the hyper-retimer can find the exact location necessary to cut the 3.5 nanoseconds delay in half. So our maximum performance is now based on 1.75 nanosecond delay, or 572 megahertz, twice the frequency of the original design. In the next section, we will look at a methodology you can use to apply hyper-pipelining to your Intel Hyperflex architecture design. Even though the hyper-retimer can move registers along a path to an ideal location, still knowing how many registers to add and where in the overall design to put them to reach a particular target performance requires an iterative process. To solve this challenge, we go back to fast-forward compile. Like with hyper-retiming, fast-forward compile also virtually implements hyper-pipelining, adding registers and locations as needed to boost the clock speed. Once complete, you will have a report that indicates where and how many new registers were added. Follow the recommendations in the report, adding the registers where indicated. Then you allow the hyper-retimer to retime those registers to where they really need to go. To use fast-forward to implement hyper-pipelining, you can follow the steps here. First, compile the design with the fast forward analysis option enabled in the QSF, or you can run it standalone. Then review the fast forward reports to figure out which path requires pipeline registers and how many stages to add. Next, insert registers by modifying your HDL code. The next step is the very important one, which is to simulate to make sure you did not change the intended functionality of your design when you added the extra registers. Then lastly, assuming your simulation was successful, recompile the design to verify your post-hyper-pipelining timing results. In the next few slides, we will go over the details of some of the steps to this flow. After running fast forward analysis, you can go to the fast forward details report to see the results. If your fast forward analysis is able to achieve a performance improvement by using hyper-pipelining, then hyper-pipelining will appear as one or more steps in the report, as shown in the screen capture. Just highlight the fast forward step that shows an estimated Fmax that is at or above your target clock rate. Then go down to the Optimizations Analyzed section to see the details of what was virtually done to your design to reach that clock speed. Keep in mind that the recommendations might be hyper-pipelining only, or they might be a combination of hyper-retiming, hyper-pipelining, and hyper-optimization modifications. Expanding the Optimizations Analyzed Cumulative tab, you can see exactly what fast-forward modifications were made, or in this case, how many and where registers were added to the design to reach that estimated Fmax value. Looking at this screen capture, we can see that 3 pipeline stages were added in the CLK clock domain. Where were they added? They were added to top-level input ports to the entity xbar_mux. In particular, they were added in between the port dn_vert and the input registers dn_reg, and the port select_vert and the input register select_reg. When adding registers, if you had to burrow down deep into your RTL to add the register stages at specific design points, that would really mute the usefulness of the recommendations. So, fast forward compile will typically add the registers at more easily accessible locations in the design, such as in between clock domains where you may already have synchronization registers, or at the inputs or outputs to the design. This is assuming you do not have internal endpoints such as asynchronous clears that prevent registers from retiming further. If this is the case, then hyper-retiming may also be required for that particular step. Like with hyper-retiming, fast forward compile provides a constraint you can use to control your hyper-pipelining analysis results. This constraint is called fast forward compile additional pipeline stages in the Intel Quartus Prime UI. The default for this setting is -1 or infinite, meaning the fast forward compile can add as many registers as it needs in order to improve performance. Using this constraint, though, you can prevent your fast forward analysis from recommending more pipeline stages than you can potentially implement. Let's say, for example, you have a true cycle latency requirement in your design or a subset of your design. If so, then there is no reason to allow fast forward compile to recommend a number of registers beyond that requirement. So you can apply this constraint and force fast forward compile to produce a solution that includes this limitation. Like the other fast forward constraints, this one can be applied globally to the entire design or locally to a specific module or instance. It is key to remember that when fast forward analysis is performed, it is only concerned with design performance, not necessarily functionality. So it only points you to a path that needs extra registers to boost that path's performance. It does not point you to all the paths that similarly need registers to maintain data synchronization. It is up to the designer with adding registers to make sure all parallel paths are pipelined with the same number of registers. And you must perform RTL simulation after your modification to verify correct functionality. Adding pipelining is very basic coding, but just as a reminder, this slide shows the basic mechanism being demonstrated on an input registered path. You break the original connection between the input and the input register. Between this connection, you add in the new register stages using signal or variable assignments within the clock process. Connect the input port to the input of the first register stage and the output of the last register stage to the input of the original register. Instead of manually coding pipeline registers each time you need to insert them, you can create a parameterized pipeline register block as shown on this slide. This way, you just instantiate the register block specifying the width and the number of pipeline stages that you need. These code examples may also be found in the Quartus software text editor in the language templates for VHDL, Verilog, and System Verilog. When adding pipeline stages, one thing of which you want to be aware is synchronizer chains. The Intel Quartus Prime Pro software automatically recognizes synchronizer chains in your logic. If a series of 3 registers are found at the entry point of a clock domain with no logic or other fan-out in between them, then synthesis tags them as a synchronizer chain. Once they are identified as a synchronizer chain, then they are endpoints and the Hyper-Retimer cannot touch them. This is desired in most cases, but say you are compiling a submodule by itself. The compiler would incorrectly identify pipeline registers you add to an input path as a synchronizer chain, when in reality they will be internal registers when the submodule is instantiated in the larger design. Thus, the timing results you get on the submodule alone would not reflect the results when added to the larger design. To fix, you can do one of 2 things. 1. Add 3 additional pipeline registers to the paths to compensate for the synchronizer chain. Or 2. Apply the synchronizer register chain length constraint to the registers or to the submodule and set it to 1. This restricts only the first register from retiming. After simulating, you want to recompile your design. Remember that fast-forward compile is only virtually implementing the design changes. So after you make your modifications, you should recompile your design and perform timing analysis to check the results. Here in the example on this slide, fast-forward compile predicted a 741 MHz clock speed if 3 registers were added. As a test, compiles were performed with 1 and 2 additional registers added. As you can see that each time a register stage was added, the Hyper-Retimer was able to boost the speed, and with the 3 registers, it was able to achieve the predicted performance of 754 MHz result. Be aware that sometimes you may need to run a seed sweep to be sure. So why may you need a seed sweep to confirm your results? Well, there is a natural variability to the place and route results of a particular design depending on its initial seed. So it is possible that some of your results might meet timing and some of the results might not. So if you compile and your result does not meet timing, you may incorrectly think that your hyper-pipelining did not work when in reality you're just seeing the low result of a particular seed. So if compile fails, you can run a few seeds, 3 to 5 is good, to see the actual range or solution space of your modified design. You can run the various seeds by changing the seed value in the Quartus Prime settings dialog box, or even easier, run them automatically using the Design Space Explorer 2 tool. Here on this slide, we show the example results of a seed sweep on our test design. If a solitary compile had to produce the results of seed number 3, then we might have assumed that the modification failed. But as you can see, running the seed sweep, we can confirm that multiple compile runs were able to meet the 741 MHz predicted by fast-forward compile. For our final section, while the tools like fast-forward compile make hyper-pipelining very easy, there are still some things you want to think about when actually implementing hyper-pipelining. In this section, we will talk about initial conditions, synchronizers and clock crossings, and then timing exceptions, all with regards to implementing hyper-pipelining. If you have chosen to use a valid signal in your design, you will need to make sure to add the same number of registers to the valid path as you do to the data path. Remember too that the first and potentially the last register in the valid pipeline have clear signals still attached in order to preserve the initial conditions. So any new registers that you add should be placed within the valid pipeline rather at the ends. Otherwise, you will have to disconnect the resets and then connect them to the new registers at the ends. Similarly, if you use asynchronous resets on any of the intermediate registers in the data path, then use care when adding new pipeline registers. You should try to add the new registers in locations such that the new registers themselves do not need asynchronous resets, and so that you do not have to move the existing asynchronous reset signals. If you continue to use synchronous clears on your design, then make sure that any new pipeline registers you add also have synchronous clear controls on them. This is due to the fact that your logic is more than likely not designed to naturally reset, so your new registers need the synchronous clears to protect your initial conditions. When performing hyperpipelining on a path that is constrained by a multi-cycle constraint, the recommendation is to remove the constraint and just add pipeline registers. For example, if you have a path that requires 2 cycles to complete the transfer, just add an additional pipeline stage to the path and remove the multi-cycle constraint. This is because there are plenty of hyper-registers in the device that are there specifically for this purpose, so any penalty you would incur, such as in resource usage, goes away. That being said, this recommendation really applies to new code. If you have existing code that uses multi-cycles, it would be a lot of work to try to go through the entire design to implement this practice. So in that case, if the path shows up as a part of a critical chain limiting performance, then you can work on replacing the constraint with pipeline registers. Adding hyperpipeline registers at a simple synchronizer circuit is easy. Just add the registers inside either the source or clock domain, and the Hyper-Retimer can move forwards or backwards to where they need to go. However, if a synchronizer has any kind of combinational logic in between the clock domains, such as the example on this slide, it makes it very difficult to describe where to put the registers. It is even worse if signals from both clock domains drive the logic cloud. This is what we call an undisciplined synchronizer. How would you tell someone to add new registers so that the registers only affect the paths between the domains while not adding latency within the domain? Ideally, all synchronizers should be well disciplined. In other words, all synchronizers should go directly from register to register across the clock domains without any logic in between. This gives a fixed location where pipeline registers can be added easily. If you have an undisciplined synchronizer, then the recommendation is to move that logic into the source or destination clock domain. When performing hyperpipelining on a path that is constrained by a false path command, it is easiest to add the new registers on the outside of the constrained path. In the first example on this slide, that would be just before register A and/or just after register B. If you do add registers within the path constrained by the false path command, then you would have to modify the constraint to move it to the innermost registers, registers C and D in the second example. Otherwise, the new registers are inside the false path exception and the retiming would not be allowed. Another option you have when using the false path constraint is using the latency insensitive argument. Adding this argument allows the Hyper-Retimer to auto-pipeline the paths to improve timing. How does this work? Well, you apply the argument to a clock domain crossing false path exception. Note, it is only valid for clock domain false paths. It provides no benefit to path-specific false paths. Once applied, during retiming, the Hyper-Retimer checks the domain crossing paths and inserts pipeline stages which will read time forwards and backwards into each domain as needed in order to meet timing. Note that each path is retimed separately according to the timing needs of that path, so each bit of a single bus might be pipelined differently. So how do you use it? Well, it works on clock domain crossings which are not being analyzed, such as between logic functions not designed to run at the same time. Let's say you have a circuit that loads coefficients into a data path. While the coefficients are being loaded, the data flow is shut down. So the receiving circuit is not sensitive to the individual coefficient data bits arriving at the same time, as the configuration logic will hold the values long enough for their propagation to complete. Thus, extra pipeline stages can be inserted in the path without breaking the design functionality. This argument should not be used on clock crossings which use any sort of clock crossing circuits such as dual clock FIFOs that are constrained with their own timing constraints such as set max and min delay, set net delay, or set max skews. The false path constraint, with or without the latency insensitive argument, will override these constraints used by the circuits, which could break their functionality. In this example, we have a clock crossing path to which the false path constraint with the latency insensitive argument is applied. Upon retiming, pipeline registers are automatically inserted into the path and retimed depending on the performance requirements of the clock domains. This concludes the online training Introduction to Hyper-Pipelining. In this course, we learned that hyper-pipelining is adding new registers to your code and then allowing the hyper-retimer to distribute the registers along the path. We learned that while you can try to do hyper-pipelining manually, fast-forward compile makes it considerably easier as it tells you exactly where to place new registers, how many to add, and how fast your clock can run with the registers added. Finally, we discovered a methodology you can follow to incorporate fast-forward compile and hyper-pipelining in your FPGA design flow. If you have more questions on using hyper-pipelining on your design, please refer to the High Performance Design Handbook. If you would like to continue in your learning of the Stratix 10 Hyperflex devices, you can view the follow-up free online training shown here. Introduction to Hyper-Optimization talks about the factors that may reduce the effectiveness of hyper-retiming and hyper-pipelining and teaches how to locate and evaluate loop structures that can reduce design performance. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed gigabit interfaces. There is a community forum, and there are hundreds of training courses available just like this one. This concludes this online training. Again, my name is Marlon Price, and I thank you for your time.